video, I'm going to be explaining another important paper with the title Graph Filtration Kernels. This paper in 2021. The majority of popular graph kernels is based on the concept of Hausler R-convolution kernel and defines graph similarities in terms of mutual substructures. In this work, we enrich these similarity measures by considering graph filtrations using meaningful orders on the set of edges, which allow to construct a sequence of nested graphs. We can consider a graph at multiple granularities. For one thing, this provides access to features and different levels of resolution. Furthermore, rather than to simply compare frequencies of features in graphs, it allows for their comparison in terms of when and for how long they exist in the sequences. So we propose a family of graph kernels that incorporate these existence intervals of features. While our approach can be applied to arbitrary graph features, we particularly highlight WL vertex labels leading to efficient kernels. We show that WL labels over certain filtrations strictly increases the expressive power over the ordinary WL procedure in terms of deciding graph isomorphism. So if we have two graphs G and G prime, then the simplified R convolution can be written as this sum, this is the kernel on the substructures. So kernels can alternatively be described by the inner product of these explicit feature vector. So, for example, a histogram kernel can be equivalently be expressed as a sum of feature frequency products. And then they talked about Wasserstein distance. The general idea of feature persistence in graph is derived from persistent homology, because you can always create a filtration on graphs like this. So it's just an ordered graph refinement that constructs a graph by gradually adding sets of edges. Add until you get the full graph. The majority of traditional graph kernels define similarity in terms of number of mutual substructures. Often this comes down to simply comparing frequencies of features. Using the concept of feature persistence, we are able to define much finer similarity measures in graphs. We achieve this by defining a distance function on histograms, which aggregate lifespans of feature occurrences. So this is here in this picture, you see, consider a simple WL label F corresponding to a vertex having exactly one neighbor. Each occurrence of this feature is individually marked in the filtration graph. You see in B that the barcode in C depicts the existence intervals of each such feature occurrence. This information is then aggregated into filtration histogram. So what is filtration histogram? You see, given a graph G together with a length K filtration and a feature F, the function maps G to its filtration histogram, which counts occurrences of F in each filtration graph. Now we can define this distance. So what is a distance function? A filtration histogram mapping. So given graphs G and G prime a filtration histogram mapping phi, together with the distance function d on associated values, the filtration histogram distance is here. The ground distance d on the Wasserstein distance defines how feature occurrences at different points in the filtration are being compared to each other. Another definition is filtration kernel, because now that we have graph G and G prime, if you have two graphs, a filtration function A, if we have a filtration function, as I said, how we construct that, and a set of features, the filtration kernel can be written like this. And they proved in the theorem the filtration kernel is positive semi-definite. Also, the filtration kernel for k equal to 1 reduces to just the histogram kernel. Then they talk about the WL method. Then some theoretical works. And then here they talk about influence of filtration length k. This is classification accuracies and standard deviation on real-world benchmarks.